So I'm Robert Watson. I'm a professor at the University of Cambridge, along with Simon Moore, and later joined by Peter Sewell and Brooks Davis and others. We've been developing the CHERI architecture for the past, I don't know how long, 15 years, in fact. And when I say others, I mean like very many others. I've not included the full co-author list, but there we are. I'm going to talk to you today a bit about the CHERI Research Center and some of the work we've been doing. CHERI Research Center is a new thing, so I'll have to explain what that is when we get started. So the Research Center was started in April of this year. It's funded by DCIP and EPSRC. We also have financial support from DARPA, ARM, Google, and CODASIP, and lots of in-kind contributions. So I thought I should particularly mention the people who wrote us letters of support, which is very much appreciated. So Capabilities Limited, CHERI Alliance, SCI, SEMI, and others. And we are roughly 40 people, most of whom are located in West Cambridge, working in and around CHERI. It's not 40 full-time people, but 40 people who are actively involved. That's 20 research staff members, 10 affiliated PhD students. Then we have a bunch of industrial and academic visitors who come and use desks in the department or meet with us and collaborate with us frequently. And then led by myself, but also Simon and Peter. We really have three goals that we laid out in our proposal is to try and get this work into real world use, right? And there's different aspects of this. And as a university, we are particularly well suited to perform certain of them in a way that complements the CHERI Alliance and the other work in this community. So one of them is kind of in the area of standards and open source and sort of infrastructure gets tacked in because you have to have 3 bullet points. The direct engagement with industrial adopters. We help people with software designs. We help people with hardware designs. We provide, reference implementations they can look at. And John was talking about some of that work earlier. And then more generally, how do we encourage the adoption? And that's through talking to the general public. It's through exercises around policy, building demonstrators. We can show things off. And I just conclude this introduction by saying, if you would like to engage with us and collaborate with us, that's what we're here for. So we're really happy to do that. And I know that many of the people in this room have already collaborated with us, which has really been a great experience. We learn a lot from doing that. So what are these general remits? Well, we do a bunch of stuff to try and facilitate adoption. And some of these things are kind of public-facing activities to support everyone. It's things like providing access to CHERI hardware. We do things like producing formal models of instruction sets and engaging with that and transitioning that technology into broad use, where in fact a bunch of the companies here are now using those formal models, which is really exciting. Being able to work closely with microarchitects at companies who are building processes or extending processes. We've done that for several companies now. It's a really enjoyable process for us because we learn a lot about industrial microprocessor design. It feeds back into our research and improves the realism, but also it helps us identify obstacles and problems where we can work on them interactively. It's a very rewarding thing. And we'll talk a little bit more, I think, about some of these other engagement activities as we go along. So I can't tell you about everything that we're doing right now. 40 people working on stuff. But let me tell you about a few things that are perhaps particularly interesting at this moment. So one of the things, here's 4 things we'll deep dive on, but one of the most important things we're doing is assisting with the process of getting RISC-V standardization sorted out. I think we were playing leading roles in it, along with several of the other people here and involved internationally. Another thing we've been doing is looking at the outcomes. So DSBD was this 4 or 5 year research program. A lot of people wrote CHERI code. They worked with CHERI for the first time. It's taking a while, but we're working through a lot of those results, both in-house ones and ones from working with many collaborators, trying to draw lessons from those and share that knowledge around. Talk a bit about that. Another policy area is around memory safety standardization. I will deep dive on that in a moment. And then I'll tell you about some awards we got because that's kind of fun. But there is a lot of other stuff, and I can't talk about those things today, but I'll hand away to a few things. We have a lot of work going around microarchitectural research. How do you improve the performance of CHERI, but also how do you use CHERI to improve the performance of other things? Like, can you use the metadata in CHERI, for example, to provide better prefetching or integrate with other parts of the microarchitecture? There's this rich evaluation of software integration. What are the actual benefits to using CHERI, C, and C++? What are the friction points? What more can we do? Because there is a lot more we think we can do with the architecture than we're doing today. Another aspect that we're spending lots of time on, won't discuss today, adversarial research. We have people who are working away looking at what is the actual benefit to CHERI in complex pieces of software. So one of our research projects for the last couple of years has been bringing the V8 language runtime, actually a high-performance language runtime used in Chrome, but also in Node.js. Language runtimes are super interesting. So CHERI should ideally support them in some way, but what security benefit does it bring when you have just-in-time compilation or you have very customized high-performance memory allocators? Analyzing that is interesting. And And then pushing quite hard on compartmentalization. And John's question earlier, memory safety is great, but what about the performance win from compartmentalization? Is something we're working on daily. So very interested in that. So let's talk about one or two of those in a little bit more detail. So how do we get into this place where we have a RISC-V international specification? As identified earlier, the standardization process is really important, right? One of the things that we require, and I think we're getting out of this community, is multiple independent supply chains for IP, for hardware designs, and so on. If you're just buying the product of one company, can you commit governments to using this kind of technology or large-scale product lines or things? No, it's really important that you have the standard to make sure you have interoperable, if you will, or consistently implemented hardware that can run software stacks. So we've been working with industrial partners. I think it's really important to highlight the leadership role they've played in this effort. Codicep, Google, SCI, SEMI, and others in trying to push this specification to reality. We're helping to do that, but I think the leadership is very much coming out of industry and the demand from industry. So, for example, we've implemented the draft specification, well, probably several versions of it by now, in our research microarchitecture CHERI tuber, which you've heard about and is also being used by others. Spending quite a lot of time maturing very specific parts of the instruction set, which we were trying to understand in the Morello exercise. Arns Morello, you've probably heard Richard and others say along the way, is a superset architecture. Sometimes it contains multiple possible design choices so that we can cross-evaluate them. And so one of the important things we've been doing for the last year is saying, well, okay, well, we had a bunch of these design choices in Morello. Which was the right one? So that is what we can embed into the public standard, the one that people will be implementing. So I think very important, it sort of illustrates the ongoing value of Morello to run large software stacks to explore design spaces. We've adapted our CHERI-based research operating system so that we can actually use a bunch of these features that aren't yet available in SCL4 or in CHERI Linux to push performance, to understand, again, this portability factor, and also to help us optimize the design and get to these performance numbers that we need to pitch the architecture. Working with lots of partners to help them mature the implementations they have. I mean, our experience generally is, you use a prototype or a new CPU for the first time in different ways, you're going to find bugs. And that's an important role we can play because we both can work with and understand the bugs across layers, and we can help figure out what the right fix is if the answer is not immediately clear. And that's what happens when you're doing new and exciting things. A bunch of the partners, industrial partners, have done things like bring us draft standard RV64Y, RV32Y support for LLVM. We help to bring maturity to that effort, validate it in various ways, QMU and so on. And I say, we're this close to having a specification that can have finalized opcodes, which is a very exciting moment. And it's, from looking purely at the application core perspective, we've really demonstrated that software portability. We can run our CHERI-based stacks with all these features, the same software image on our research microarchitecture tuber, on the Codicep X730, and on CV86 CHERI from Capabilities Limited. And the demos all run, the tools run. As that is an outstanding success from a standardization process that it actually works. What is arguably almost the first time. So. Some other stuff. I was talking a bit about learnings from DSBD. We're spending quite a lot of time on that. So the start of DSBD, we had some research implementations and so on, it's 5-6 years ago. And now we have multiple mature industry-developed microarchitectures from microcontrollers up through application cores. So we need to try and learn from that process and share those learnings through publications and reports. Another area where we've learned a ton is, we started that process. Like maybe if we were lucky, might have gotten to 10 million lines of code running on CHERI, PureCat, probably 5. Anyway, at the end of it, we can count 200 to 250 million lines, and that excludes the lines of code that have been adapted by other people to run on the platform. And that is a completely different world in terms of understanding the richness, the generality, the limitations, all that stuff. So we're distilling this information. We're starting to push out new technical reports. I guess a couple of weeks ago, we pushed out this CHERI roadmap for Linux, which is a collaborative effort across Codicep, ARM, Google, and others, pulling together a longer-term strategy based on a kind of a consensus building and learning from the BSD experience. We're in the middle of updating our CHERI C++ Programmer's Guide, improving a lot of the advice. We've learned a lot about porting software, taking away some of the rough edges, but also trying to write down more of what we meant now that we understand what we meant and what we meant to say, or maybe now know we should have meant to say. Anyway, lots of work there. We're generally developing these documents as living documents rather than pushing out University of Cambridge tech reports, which is what we do before. We'll have them up. They'll be in GitHub, MDBook versions that are updated live. And we really welcome both the improved access that provides, but also your feedback and contributions. We're a constant search of co-authors who want to contribute new insights and that kind of thing. So please do. thought I would spend a little bit of time talking about memory safety standardization. This is an area of public policy intervention, which then leads into some specific technical activities. So in the abstract, one of our goals in doing CHERI is to get to what we sort of term universal strong memory safety. This is every device that you have access to having the kind of protections that CHERI is affording on the memory safety side, and ideally on the compartmentalization side as well. But there's actually a bunch of other technologies, as we talked about, competing in this space, not probabilistic, sort of weaker mitigation technologies, but actually strong memory safety properties coming out of languages like Rust or the use of formal methods. And so we would like to live in a world where we can argue for total adoption in all devices. In 30 years, 5 years, 10 years for various things. Some devices live in the field for 30 years. So, if you want to get all the devices or longer, it's going to take a while. But we want to try and get policy interventions and technical interventions that get there. And one interesting, I think, moral, in fact, of parts of DSPD is it's very hard to push a technology onto vendors. What you want to do is push requirements onto vendors and allow them to decide how to meet those requirements. And across those different approaches to strong memory safety, there are trade-offs, right? They have very different deployment narratives, very different use cases. Even in one product, you might use several of those different technologies, maybe composed or maybe in different parts of them. And we have to recognize that. So the requirement we're looking then to push is a requirement for memory safety. And there is some bad news about strong memory safety, recent news from Apple and others aside, and that's that the incentives appear to be a bit mixed. So in order to get to the point where these things are in consistent, strong use, you're basically lifting the level of industrial best practice. Industrial best practice today is to put in memory safety mitigation mechanisms, is to use high-level languages for places where security is less important and low-level languages for places where security is most important. It's the very judicious use of formal methods, maybe in your secure enclave, but perhaps nowhere else. And it's maybe Rust for new code, but maybe not the existing code. So we need to really lift that practice and help educate people about that to get there. Another thing is that the resistance to vulnerabilities actually has relatively little perceived demand in the marketplace. If you ask someone, do you want the phone with more battery life or do you want the phone with more security? They will pick battery life. It's just inevitable. And that means that even the consumers who think they have very strong security demands are limited by the market to only getting devices that meet weak security demands. So I think we hope that there is, in fact, quite a lot of latent demand coming out of critical national infrastructure, national security, companies that actually do have significant financial loss opportunities as a result of poor memory safety, and yet that demand is not well expressed, right? And it's not well handled. We need to try and focus that. Perhaps more importantly, there is a nasty opportunity cost problem. It's not that the companies that we talk to about adopting strong memory safety don't want to do it. It's just that they can make a lot more money by not doing it, right? The cost of vulnerability management versus, the cost of rewriting your entire OS environment in Rust or, deploying new generations of hardware. That's a tricky trade-off at all parts of the supply chain, from hardware supply all the way through to software on top. And then if this is a multi-decade strategy, that is difficult for governments who are supposed to think about the long term, let alone a company that is, your product ship time is in 9 months. So, no hope for 5-year, hardware delivery. So the result is I'm sort of a little bit critical, but token gestures or, very focused efforts in very specific important places, but not an attempt to get to universal strong memory safety. And you have to have a slightly hyperbolic slide. So one of the things that it's just a rule. If you are going to industry, you will often hear things like, I'm sorry, we can't afford a 2% increase in DRAM access patterns because that means across our data center an increase of 1.5% of energy use or something like that. You're right. It does cause that increase in energy use. That is hard to eliminate with any of the technologies we're talking about. So they just, sorry, that's an unaffordable energy cost. Sorry. And then they turn around and we bought a nuclear power plant. So that's tricky. But I think there's an important lesson there, which is it's about incentives, right? There's an incentive to use more energy for whatever people might be focusing on today. I can't imagine what we're talking about. And there isn't really the same incentive there to deploy some of these security technologies if they have significant opportunity cost or significant energy use. So we need to focus on incentives. It's always economics. So we wrote an article with a bunch of other people, including from ARM and Google and Microsoft, February of this year, basically arguing, well, there's a bunch of missing demand, and perhaps it's there but not well expressed. And we need some standardization of not, we make it standard that memory safe is everywhere, but we explain what it means to be memory safe. If you went to a company today and said, give me a memory safe product, I have no idea what you would get. But we need to enable all these things, industrial best practice, subsidies, tax incentives, all that stuff. If you have coming a liability regime, then how do safe harbors work? Maybe you get into one by using strong memory safety, a ton of stuff. And one of the things we argued, I think, for is, actually the creation of a framework to discuss memory safety, about which there is considerable disagreement on what that could mean, even among people who are huge fans of it. I have a slide on that in just a moment. And then, the steps we have to take to get there. And part of that goal, I think, although we like CHERI quite a lot, is to figure out how to do it in a technology neutral way. Because if you're expressing requirements for government procurement, you can't say you must buy the Armorello thing or the SCI, whatever thing, it has to be a set of requirements that can be met in different kinds of ways, and to allow the possibility of innovation too. Which kind of led us to this annoying question, which is, what is memory safety? I suggested there's some disagreement. So, the starting point for us is to say, well, what does CHERI think memory safety is? And that was an awkward question, because we have a very kind of empirical view of memory safety. We built a system to do memory safety things. That must be what memory safety is. And I think we recognize the slight paucity of that view. But for us then, the starting point is actually to write down what we now realize that we meant by CHERI memory safety, which is very much a lesson of doing all the software integration. It was a co-design. We didn't understand when we started what memory safety for C would be. So actually writing down requirements then would not have been a very useful activity. Now that we've worked with it extensively, we kind of understand what we want. And some of that stuff is really CHERI specific. It's like, sub-allocation. You have a chunk of memory, you break it up into more objects to pass on to more things. Most memory-safe languages don't talk about that. There are objects in the language. They come out of magic, right? And like C is kind of like that in an official sense, but you implement malloc in C. And many applications have their own memory allocators, so you have to get there. Anyway, suffice to say, there are a bunch of interesting questions, and we probably have really interesting things to say. So there's an effort now started, thanks to NCSC and DCIT and others inside ETSI, which is a European standards organization, to try and standardize the definitions of memory safety. This is clearly just the starting point. If you want to procure a memory safe system, saying here are the definitions is not the end of the story, but it is the beginning of the story, because we have to agree on, if not on one thing that it means, then a space of things that are all acceptable and that we're willing to consider that. And so first meetings kicked off in September. Lots of online discussion since then, and the goal is to have a really substantial draft, something very probably like pushing off the mature end of draft at the end of March. We'll see how that goes. Some of that discussion is solely inside ETSI. You must be a member to participate in that, but a lot of it is actually brainstorming, workshopping ideas, and that can be done entirely outside of it. And this is important because it can feed into future, what I call supply chains of standards, right? People are going to be writing standards that must refer now to memory safety. So someone's going to have to write those things. Probably won't be us, but it is a necessary step to get there. Yeah, so I told you how to slide on the beep. Okay, but now I'm going to abuse that situation by 4 wrapping up slides. So first, just a quicker slide for those of you who weren't. Sorry, Mike. For those of you who weren't at HISC yesterday, I was not at HISC yesterday. Conrad thoughtfully sent me this copy of the slide. This is Dave Kladdemacher's slide. He is the VP of Security Engineering and so on for Android at Google. And this slide, I don't know if you can read it, it leaves some of us with slight reservations, but let's set aside skepticism for a moment. What the slide is saying is, okay, well, in the future, how do you get strong memory safety everywhere? Well, way one is to use CHERI for a bunch of your critical source code bases, lots of things like operating systems and so on. Way two is that, AI is an amazing technique, and we use it to start rewriting some of our software bases, but probably not all of them, especially not the challenging ones, into Rust. Now, negative way to view this. Some of us are skeptical about generative AI and its ability to solve all problems, but Google is not. Google was heavily invested in using technologies like Gen AI. And if you find that your VP of engineering has put Gen AI alongside CHERI as the solution to the memory safety problem, that's a very powerful statement. And it's something I think that we should reflect on and figure out how to use. And, I think as Jeremy says, like carefully moderate hype and, all that stuff. But it's a powerful thing. And I think it's interesting that we're seeing the VPs of companies like Google now talking about CHERI as a solution to those problems. Wrapping up slide 2. So we were very proud. We received 2 different IEEE Security and Privacy Awards this year. One was the Test of Time Award for our original CHERI compartmentalization paper in 2015. It was great. And then actually we received the Best Paper of the Year award from IEEE Security and Privacy for 2024. We received that, I guess, a couple of months ago. So we're very pleased about that. And you see that was a fast wrapping up slide. Another wrapping up slide. We hope very much that you're going to come join us at CHERI Blossoms 2026 in Cambridge in March. The dates are online. Really looking forward to hosting everyone there. It's CHERI's 15th birthday party. In fact, it was probably CHERI's 15th birthday in the last week or two. And so it's super, satisfactory thing, but come have a party with us at CHERI Blossoms. It'll be fun. So another wrapping up slide. So CHERI research, certain liberties can be taken. Anyway, So the CHERI Research Centre is now extant. Very much appreciate the support from UKRI, from DCIT, and we're doing a bunch of stuff. We're trying to really propel the technology forward. Obviously, we live at the research end of that transition story, but it is clear that more research is needed. You know, how do you get the performance in certain use cases? What is CHERI good for? How do we integrate CHERI with things like Rust? I think is a really critical question. If Rust is already being declared a requirement for many devices, you can't make it a choice, CHERI or Rust, right? But I think actually, you know, CHERI brings a lot to the Rust story. So there should be good stuff. Right? And we're eager to try and do that. And I think also technical barriers to adoption, we're obviously happy to engage with and we do, but the non-technical ones, like the procurement aspect, are really important. That's the last slide. But I thought I would just stick this one up in case there was kind of time to mull the things. You know, there have been past failures. Thank you very much.